Dominguez, and I'm an associate professor at the Technical University of Madrid, Diseño Industrial, and I'm going to present briefly Hyperion technology and based on a microconcentrator PV module that integrates tracking internally and can capture the diffuse light. I will firstly introduce why microconcentrators matter, why they are a disruptive technology here, and I will then describe one particular micro CPV technology that integrates several of these advantages, which is the InsoLight module. And then I will talk about the pilot installation that Nacho didn't want to spoil, and that has been installed at the rooftop of the Solar Energy Institute to help demonstrate this technology within the Hyperion project. Well, the context of this talk can be reduced to a single challenge. How can we keep reducing the cost of solar electricity when the cost of PV modules is already extremely optimized? And what is more, the cost of PV modules is a shrinking fraction of the total system cost of a PV plant, less than 25%, for instance, in utility scale PV plants in the US, or even less in rooftops. Therefore, further reductions in module cost will have a limited impact in the price of solar electricity. So the alternative to cost reduction is increasing the efficiency of the modules. And this is where many PV manufacturers are engaged now. This was actually the promise of concentrator photovoltaics, which is an old well-known technology from the 70s, where the solar cell is not directly exposed to sunlight, but some kind of optical system that concentrates the light onto a much smaller solar cell. Let me take the pointer here. Okay, so you can see a much smaller solar cell. So this allows using high efficiency solar cells that are too expensive to use them in flat plate. Currently, the record is around 47%. These are called multi-junction solar cells. But also this concentrated light increases the efficiency fundamentally of the solar cell because of the increase in voltage. So as a result, we have a PV system with a maximum yield per area. However, this technology comes with drawbacks, which is why we don't see them as the dominant technology, right? First, systems are more complex and more expensive, so the capex is higher than flat plate. Also, the concentrator optics I talked about can only collect light that comes from a very narrow angle. And for this reason, CPV modules cannot collect diffuse light and need external structures to aim at the sun precisely throughout the day. And because of these bulky structures, they usually cannot be used in rooftop applications where the high power per area that CPV has would have most of the value. And here is where microconcentrators offer some solutions. Let's see how. Microconcentration basically refers to reducing cell size below the millimeter range and scale the rest of the components accordingly. A reduction of n times of length involves an increase of n squared of components. This increase in complexity comes with several fundamental gains in efficiency related to the reduction of the optical path first, and then to the reduced amount of power that each solar cell has to manage. You also reduce the bill of materials and the embedded energy and therefore the carbon footprint. This is an important advantage here, and the form factor of the module can be reduced to create thin, lightweight modules. As I said, in CPV, the diffuse irradiance is transmitted by the primary optics. Only direct irradiance is concentrated by the primary optics, but the diffuse light is also transmitted, but to the backplane and is not captured by the concentrator cells. So in micro CPV, where the optical system is so thin, it's interesting to propose hybrid architectures like this. You can see from the Nagaoka University of Technology, where the backplane is covered not only with these small CPV cells, but also with larger non-concentrating cells like silicon or thin film solar cells that will capture this diffuse light. This increases energy yield, especially in locations with low direct insolation, like, for instance, most of Europe. And one last innovation that that micro CPV brings is that of integrated tracking, which avoids the need of these bulky external tracking structures. Modules are stationary, and some specially designed optics will manage to concentrate light at different angles of incidence. So to achieve this internal tracking as the sun moves, either the solar cell or the optics have to be shifted to find the focus as the sun moves. So this basically is enabling a fixed mount, a static mount, and the rooftop market, which otherwise would be not accessible by CPV. And this is where the Swiss company Insolite comes and combines all these concepts to create this hybrid micro CPV module that includes a hybrid version. In some versions is hybrid and includes a flat plate backplane that is able to collect diffuse light. As you can see, it uses a static installation. How is this integrated tracking enabled? It is based on this special design of biconvex lenses that you can see also here in a real picture. These lenses concentrate direct light on 3-5 multi-junction solar cells with high efficiency, but also the diffuse light that will go out of these concentrator lenses is captured by silicon cells that are non-concentrated ones. When the sun moves and the angle of incidence, AOI, varies, it's not normal anymore to the module, the backplane is shifted to find the new focus for the concentrator lenses. And this movement is very, very small, in the range of millimeters. Actually, the control system, we can say, is hybrid as well, and it uses both ephemeris, solar ephemeris, and some feedback loop from PSD sensors. So as a result, we have a hybrid module with two separate outputs for the silicon cells in red and for the 3-5 cells in gray. As you can see, these are some actual measurements in watts per square meter of power density output. You can note that the CPV part will contribute in a clear sky day like this, will contribute most of the energy, but when this internal tracking stops, because of the optical design has some limits, this has an angle of incidence range, a tracking range of 55 degrees. Then the tracking stops, and you can see as the sunset comes, all the light, both diffuse and direct, goes to the silicon cells. As a result, the energy yield per area can be increased with respect to conventional silicon modules, not only in typical high DNI locations like Southern Europe, but also in regions with a high diffuse fraction like Northern Europe. You can see Lausanne here, for instance. You can check this publication for more details on this. In an alternative architecture that Laurent Coulot will talk about, they have created also an architecture with a transparent backplane that would allow for a dual land use, especially because the diffuse light will pass through the module and can illuminate, for instance, crops for agro-photovoltaic applications. A pilot installation, a pilot plant of these InsoLight modules has been installed at the rooftop of our institute as part of the efforts of the Hyperion project to take this technology to industrial maturity. And the plant holds the first generation of InsoLight modules. There will be a second generation within the project in a modular structure, so it can be also it can be easily extended. Some of these modules are translucent, you can see here, and some are hybrid with silicon cells. And the structure faces south and has a fixed tilt of 30 degrees. The objective here is to monitor both outputs of the PV array, CPV and silicon, to obtain useful information on the performance of the technology, especially concerning the effectiveness of the integrated tracking. The modules include internal sensors that measure module current and voltage, as well as tracking coordinates. Well, to complete this monitoring, we assess the solar resource with our own meteorological station, equipped with accurate pyranometers and p-heliometers to characterize both direct and diffuse components of the global irradiance, which is key to understand the behavior of this architecture. You can see here the layout. This is a configuration based on microinverters. One microinverter per module, and all this, sorry, in the translucent version, and 2 microinverters for the 2 outputs of the hybrid modules. All inverters are connected to the AC grid, are injecting the energy, and can be monitored using the gateway of the vendor of the inverters. The modules use some internal electronics to control and to monitor the modules, and also produce the actuation, and they need some external power supplies. And this monitoring and external power supply is provided through a canvas, using this daisy chain configuration for up to 4 modules each. This gateway computer controls and monitor the whole array, and this computer allows the user to log and monitor module performance and send commands to the installation through a web interface. You can see here a picture of the control box besides the installation that holds all the necessary adapters, power supplies, and gateways that my colleague Steve Askins will show you live in a few moments. And that's all from my side. Thank you.
Thank you very much, Cesar, for the presentation. Now we will move to the next speaker, which is Jacques Debras from CSEM. He will present the Hyperion Consortium, the project that is supporting all this activity. Jacques, please, the floor is yours.
You can hear me now?
Yeah, very well.
Fantastic. Let me know when you can see the presentation.
Yeah, we can.
Fantastic. So thank you, Ignacio, for the presentation. So it's my pleasure to present to you a bit the general concept of the project, the Hyperion project. So my name is Jacques Debras. I'm from CSEM, and I'm coordinating the Hyperion project. So first, Hyperion projects at a glance, a few numbers to give you an idea. It's a 4-year project. It started in August 2019 and will end in 2023. So we are currently in the middle of the project somehow. We received a 10.6 million euro grant that has been distributed among the 16 partners originating from 10 countries. We have partners originating from industry, also solar installers and research centers. The challenge of this EU call is to increase the competitiveness of the European PV manufacturing industry. with innovative solutions. So Cesar just presented the concept of the hybrid modules. And to achieve this challenge, we have 3 main objectives in the project. So the first one is to demonstrate at the pilot line level this hybrid module with the potential to scale up to the gigawatt size. The second one is to have a blueprint ready for gigawatt scaling. So to achieve this, we first need to demonstrate tailored assembly techniques, also to build the production line. So Delphine will show you later some picture and the concept. And last, perform qualification tests and to establish the relevant norms to be able to measure these special modules. And the last objective is to demonstrate 50% more energy than conventional silicon modules. To achieve this, we need to achieve a different key performance indicator. So in particular, above 30% efficiency in standard test condition under direct sunlight, 15% for the backplane for the silicon cells, and 25 years lifetime, and of course ease of assembly to demonstrate the industrialization of this technology. We have partners from many horizons, as I mentioned before. So in the center of this, we have the technological startup Insolite that brought IP to develop this product. Around around Insolite, we have people from research centers, so UPM Fraunhofer that are organizing this nice workshop. We also have the University of Lodz and CSEM. We also have the chance to have on board many big industrial companies, including Mondragon Assembly, 3S Solar Plus, Hyperion, Argotec, IQE, and Sonsbo. I will comment a bit more in the next slide about the respective role of these companies. We also have the chance to have many solar installers from different countries. So Muon Electric in Portugal, Milio Studio in France, and Engie Laborelec in Belgium. And to coordinate dissemination and communication of the Hyperion project, we have ELOP from France and Compass from Switzerland on board. So what are the roles of the partner? And to understand what they do, maybe just this one slide on the workflow. So you see, of course, there are many work packages, but what matters is you have this 3 work package here in the square that will lead to the last generation of this hybrid module. Insolite is coordinating here the work, and you see the role of the different partners. So on work package 2, we are designing the final gen. Sonsbo here is developing the actuators. IQE, Xeleprint, and Argotec are working on the multi-junction cells and the print to circuit board. And Mondragon Assembly is designing and developing the machines for the installation for the pilot line. So this will be transferred to the pilot line in Neuchâtel that will be operated by Insolite and CSEM. In this work package 6, Fraunhofer and UPM will develop the standards to measure these modules and also do all the reliability assessments to demonstrate 25 years operation. And finally, this blueprint validation will be done in the field. So we have chance to have installers that will target different type of installation. So Muon is more about autonomous building. Milio Studio rooftop are more rooftop installers, and Engie more focusing on utility scale. 3S Solar Plus is a module manufacturer, so they will evaluate from the manufacturing point of view the hybrid technology. And the University of Lodz, he's doing the life cycle assessment. And around this, of course, always dissemination, which is a very important task. So this is all on my side. I want to thank all these partners that are bringing a lot of work and valuable work to this project, and the EU Commission for funding this work. I don't know if there are questions. Ask you if you want to.
Okay, thank you very much, Jacques. We will pass first to the virtual visit, and then we will have some time for question and answers after the visit.
Okay.
So let's move on to the core part of this workshop, which is the virtual visit. We will have our colleagues in the rooftops here in Madrid and also in Fraunhofer. We will start with Steve asking that we will present us the pilot installation that we have in the rooftop of the main headquarters of the Solar Energy Institute. So, Jax,
yep.
If you can give up sharing the screen, sorry.
Sorry. Yeah, of course. Wait, 1 second. I have a bit problem. You can do it yourself to remove my. Wait. I have difficulty here. Yeah, here. Stop share. Thanks.
Okay, great.
Sorry.
So hello, Steve. Are you there?
Hi. Welcome to the rooftop of the Solar Energy Institute here in Madrid. This is the rooftop of our main headquarters and where we do most of our outdoor testing. You can see we have a couple of different kinds of equipment, including a fairly large solar array that is actually over 20 years old now, still producing power. The institute is located in the north of Madrid. If you look off in this direction today, it's quite hazy, but on clear days you can see towards the Sierra de Guadarrama, about 50 kilometers north of Madrid. And we are located in a place called University City, which is an area that has, it's a large campus that has faculties from many different universities, some of the main universities of Madrid. And we're actually located within the campus of the Communication School of the Madrid Technical University, UPM. So as I said, we do a lot of types of measurement up here on the roof for our research. In the CPV group, one of our main pieces of equipment is our 2-axis laboratory tracker. So you can see I have set up right now a couple Insulite modules that I'm measuring. And I also put up here just a conventional CPV module for comparison. This is a module that we have from a project maybe about 10 years ago that we helped the company develop. It's a 500X module with 5mm solar cells. And so this module, in order to generate electricity, since it's CPV, since it's concentrating the light, needs to be pointing directly at the sun. As you can see, this tracker is constantly making small movements and maintaining the angle between the perpendicular to this glass and the sun within plus or minus a 1/10 of a degree or so. In order to measure, normally we would have this connected to an IV measurement system, which is below us in the lab. Right now, I'm measuring, as I said, these 2 Insulite modules. Obviously, the Insulite modules do not need a tracker, as Cesar already explained to you. But for power rating and for determining sort of their maximum efficiency when they do have 0 angle of incidence, it's also useful to take measurements on the tracker. Juan Martinez from Fraunhofer will also talk about that in just a few minutes. But I think if we come around here, probably the most interesting thing to show now would be the pilot installation that we have now. Since March of this year, we installed an 8-module array of Insulite modules that you can see here that are online and producing power. So I think Arash is switching now to show you some of the online output. You can see there's different powers. The modules towards the right are producing a little bit more power because they are the latest ones. We have a mix of different batches here. But coming back to the video, as you see, these modules here are mounted in a fixed tilt position in a normal type of structure that you would mount the flat plate panels like the ones behind them, and they are able to produce power through CPV using their internal tracking system. So right now the sun is coming at an angle maybe of 10 degrees. These small hexagonal optics, which have 2 optical surfaces, are creating a focused spot of light that's not now directly beneath the lens, but is slightly offset. And the entire backplane of each module is moving around in order to follow the light. So I think to help explain this a little bit better, we did prepare a time-lapse video of this array over the course of a day, using both a wide-angle camera as well as this small microscope to focus on the cells. So why don't we see that video now? And then after that, I'm going to take you around behind the array and talk a little bit more in detail about some things.
Well, this is the time lapse. You can see in the upper left part of the image an overall view of the rooftop, and a camera is placed in this red cycle that shows the detail of a few cells and lens during the day doing the tracking. So this part of the day, the tracker is engaging. Now it's already tracking. So you can see how the backplane, in this case, this is the hybrid type. You can see the micro CPV cells, but also the silicon cells in the rear part of the backplane. So during the whole day, just by moving a few millimeters, less than 15 millimeters is enough to track the sun for this tracking range that Cesar explained before. I will also talk a little bit about that in my talk this afternoon. So now it's approaching the tracking limit. So once it is beyond the tracking limit, the DNI is transferred to the secondary cells, to the silicon cells. And well, of course, during the night, it comes to the stop position.
Okay, I hope that that helped help you see a little bit more visually how these things work. And now, as I said, we're looking from behind the array now. One thing I didn't mention before is we actually have a mix of types of modules on this array. So the 4 center modules are hybrid modules. As I'm sure Cesar discussed, we have these modules have great power, not only using the high efficiency 3-5 cells with the concentration system, but also have surrounding and behind the modules. As you can see here, they have silicon cells. This one is using half-cut 6-inch heterojunction monocrystalline cells. And so those cells generate power from whichever light isn't being concentrated onto the cell. So when the system is tracking, like now, all of the direct light is going to the cell, to the CPV cells. But there is some light, diffuse light, being cast by the rest of the sky that is also going through the optics and through different angles and generating electricity by falling onto the silicon cells. On the other hand, here we have a translucent module. So this is a module that's virtually the same, except with the silicon cells removed. And so in this case, we let the diffuse light pass through. So if I put my hand under here, you can see I have sort of an area that's not completely shadowed and not completely illuminated. And here we have the illumination just from the sky. If you look through, you can see the blue of the sky, but you don't see the sun, because all of the light coming from the sun is again falling on these cells. If you zoom in, Guido, you can see quite well how these cells are within LED-like packages. They're 1 millimeter cells that are with a small dome type secondary optic and surface mounted on the back of this piece of glass. So this piece of glass is what moves, and it's also the substrate. So the way these cells are connected is that onto this piece of glass we have screen printed this entire circuit that connects the thousands of cells that make up the module, and then those packages are surface mounted on there. We can also take a look at the actuation system. So these actuators are custom developed within the Hyperion project from a partner, Sonsvos, which is an automotive supplier. So they're building off automotive type technologies for these small electrical actuators. You can see there's actually 1, 2, 3 actuators, even though the movement is in only 2 degrees of freedom. So the back of the module can move up and down in this way, or left and right. But we need 3 actuators in order to keep it mechanically stable. The actuators are connected to this junction box. Inside there is a small microprocessor, obviously, which is the brains behind the tracking. And if you take a look, the DC output from these CPV cells, which is here, is actually coming out of this junction box as well. That's because the tracking system is monitoring at all times the power produced by the module in order to use a closed loop approach and maximize the power by making small adjustments in the tracking. For this pilot line, we decided to use microinverters to provide a load for the modules and also to then take that energy produced and dump it into our local grid. You can see we have here an N-phase IQ7 microinverter. It's been a fairly simple and modular way to get the pilot up and running, allow us to remove modules and place them back. And so it provides the load as well as has its own monitoring function. If in the case of the hybrid modules, I don't think you can see from that angle, but there's actually 2 microinverters per module, because the hybrid modules are 4-terminal devices. There's no electrical connection between the silicon cells and the CPV cells. And that's important because, I mean, really they make power on different time scales. So if the module is out of range in the early morning and the late evening, then all of the energy is produced by the silicon cells. You wouldn't want those to be limited by the CPV cells. So I think that's a good time now to go over to Juan Martinez in Fraunhofer ISE in Freiburg. He's going to show you their pilot installation, which is also an 8-module pilot installation, but with some differences. He's going to explain and go a little bit more depth in how we do outdoor rating of these modules.
Okay, Steve, thank you very much for your great presentation. Now let's move very fast to Germany, to the south of Germany, Freiburg. Our colleague Juan Martinez is there. Juan, how are you doing? Are you ready?
Hello, everyone. Can you hear me?
Very well.
Perfect. So thank you very much for passing the feed to us. Now we are lightning speed here in Germany, Freiburg, Germany, to be more precise, in Fraunhofer ISE. This is our facility where we carry out, as Steve mentioned, all our outdoor testing. Here we have our dual axis tracker. And well, first of all, I want to just give you a quick view of the very nice infrastructure we have around us. So if we can just look around, we have all these labs, for instance, where we have calibration laboratories for cells and modules and other facilities. And as well, you can see the mountains where our competitors, the wind generators, are not sleeping, so therefore we cannot either. And well, this is what I want to talk to you about, like the activities that we carry out at Fraunhofer ISE. And for instance, as I was saying, in this high precision dual axis tracker, which follows the sun during the day with a precision of around plus minus 1.1 degrees, we have all the infrastructure required to perform outdoor rating of CPV modules. And as you can see, we have several sensors, which I will introduce to you. For example, very important is to be able to measure the global irradiance that falls onto the PV plane. And as you can see above there, we have 2 pyranometers. Right next to them, we have this big device with this like sort of cannon, which is actually measuring the spectral irradiance of the direct normal irradiance that falls onto the tracker. As well, because we're interested in the spectrum of the sun, we also have other devices which are called component cells in these black tubes that you can see. We have a CPV solar cell that is absorbing a part of the spectrum, and in this way we're able to assess the spectral content of radiance and compare it to our measurements with a spectroradiometer, as I just mentioned. So this is also part of the sensors that we have, and as well as the direct spectrum, we can also assess in the same way the global spectrum by using these component cells that are not collimated, but rather flat plate cells, as you can see here on the top. And that way we can also assess the global spectrum. Very important, I skipped that one, but it's just as important. If we come here, we can see the pyrheliometers that we use to measure the direct irradiance broadband. So that's, of course, a must to have when you want to perform an efficiency rating of a concentrator photovoltaic module. As you can see also, if we step back a little bit and take a look at the tracker, then you can see that we have several types of modules mounted. And well, this is because we do our own developments here about CPV technologies, but also we have other technologies. For example, regarding the Hyperion project, we have here mounted the Hyperion module, which is in this dual axis tracker in order to be able to perform a rating and then to be able to compare the performance with the procedure that we have as well developed with the performance of the modules on fixed tilt planar tracking, as Steve and Cesar had explained previously very nicely. So I think this is basically everything that I have to show you here in our dual axis tracker. Perhaps as we walk down to see the installation, I can also point to you to these other sensors that we have mounted on top, which are spectroradiometers for global horizontal irradiance, as well as global horizontal irradiance broadband, and also our weather station, because it's also very important to be able to measure the ambient temperature and the wind speed. So let's go down and take a look at the installation from the Hyperion project. Follow me, please. So here we have it. These are the Hyperion modules. And right now we have 9 of them mounted on this fixed tilt rack facing south, tilted 32 degrees. And well, as Steve mentioned already, there's 2 types of Hyperion modules right now. We have the hybrid ones, which use the planar tracking with CPV solar cells, as well as silicon solar cells to capture the diffuse light. And we also have on the left side, the translucent modules, which are interesting for applications where you want to control the light that can go through the module, for instance, for agriculture, but you also want to generate high efficiency PV power. And well, this is the installation that we have here in Freiburg. And if you follow me, or well, actually, if you point to the top of the rack, you can see that we have 2 sensors there. And this is one pyranometer that will allow us to measure the global horizontal irradiance falling onto the fixed tilt plane, as well as on the right side, we have a reference solar cell sensor so that we can make the comparison between using one or the other type of sensor when we perform ratings. We also have the same upstairs in the tracker where we can compare one type of sensor with respect to the other when we do a rating and able to say what's necessary and what's not, on what the uncertainties are in this case. As well, I just show you the measurement devices for the irradiance on the front, but we as well measure the irradiance on the back side, because as Steve said, we have bifacial solar cells in the hybrid modules, as you can see, for instance, in this module, and also the ones on the left side here from the back. Therefore, we have the same 2 types of sensors, a pyranometer to measure the reflected radiance from the ground, and also a reference cell sensor to do the same. The way we actually monitor these modules is that we have, as you can see, a lot of cables. And for instance, this type of cables that are hanging here, they are used for communication and to be able to send all the control signals to the modules to be able to track the sun during the day. But we have, of course, to connect them electrically to a controller to be able to monitor how much power we're generating. And these are the cables that come down here and follow all the way into our electrical cabinets, where we actually have all the control instruments. So if we come around here, then we can see inside where we have these solar charge controllers, which perform MPP tracking for the modules. And this way we are able to measure the voltage, the current, and therefore we obtain the power at the maximum power point in the IV curve of every module, either CPV or silicon. And something very important to mention here is that in contrast with the approach followed by Inselite and UPM, where they use microinverters to do the monitoring in AC, we kept all the monitoring done in DC. So all the electric power that comes here is DC. It's MPP tracked here by the solar chargers, and then the power is transferred onto these solar resistors, where we dump the power, and that's basically how the system is working at the moment. And well, we have right now our modules generating power from the sun. And then we also mentioned that we have developed a power rating procedure for hybrid CPV PV modules. And this is basically, in a nutshell, a summary of how the procedure works. So the first step is, of course, to measure the outdoor light IV curves of the CPV and of the PV solar cells in the module, as I have shown above, that we have the two types. And then we have to define what the standard test conditions for the module are, and also what filtering criteria we will use in order to be able to reproduce the conditions that are achieved in the lab. So after that, then it's only a matter of following the already established standard procedures from the International Electrotechnical Commission for CPV, for flat plate PV, and for bifacial PV, as well as with some adaptations we had to develop in this work by adjusting these procedures to the hybrid CPV PV technologies. And if you want to learn more about this, well, in the afternoon session, my colleague Gerald Sifa and myself, we will be talking a little bit more about CPV solar cells as well as hybrid CPV PV technology, and we will give you more insights about that. So it would be great if you can stay here with us and continue to join the feed. So this is us. This is it from Fraunhofer ISE side, and I would like to send the feedback to Steve. Thank you.
Thank you very much, Juan. It was really nice to see your facilities and all your capability for outdoor characterization. Now we will go back here to our lab. This won't be a live connection because it was quite difficult for us to move all the installation for recording and broadcasting in live from the rooftop to our lab. So now we will present a recorded video. We recorded it yesterday in order to show you also how to measure, how to characterize these models indoors in the labs. Again, Steve Askin will present this facility, this solar simulator for doing this stuff. So please, intro video.
Okay, now that you've seen the pilot installations here at UPM and at Fraunhofer and seen a little bit how we measure the modules outdoors, we wanted to take you down here into our lab, which is one level beneath the rooftop testing area, where we have our solar simulator. This is a solar simulator that was developed by the UPM specifically for measuring concentrator photovoltaics. And actually it has been licensed to a UPM spin-off called SAV. And for indoor testing of any type of photovoltaic module, what we need to do is create, obviously, a light source. And that light source has to be sufficiently similar to the sun. So we create usually a flash of light. That flash of light causes the module to generate electricity for just a short time, and we capture that generation as an IV curve, and we can characterize the device. In the case of concentrator photovoltaics, we have an additional property to worry about, which is the angular characteristics of the light. So concentrator modules, since they have an optical system, can basically only receive light within a small family of angles, as if it was coming directly from the sun. So I'm going to show you now how we can reproduce that in our lab. So if you can come a little bit closer in. So basically what we do is we use a large area collimating optic. If you can look over this way, you see this circular mirror, and I guess you can probably see me reflected in it. It looks almost flat, but it's actually a parabola with a 2-meter diameter and a 6-meter focal distance. So if we place a compact flash at the focus of this parabola, that flash will create divergent rays, but those rays, when they reflect back off of this mirror towards me, are now parallel to each other, or in other words, it is collimated. And if we come this way, we can see the area that is illuminated. So we basically, in this plane, we have a 2-meter circle of light that is direct light, collimated flashlight. We can also see here behind this screen the flash lamp, which, as I said, is a compact xenon strobe, only about 65 millimeters in diameter. If you look geometrically, if you take a 65 millimeter circle and put it at 6 meters, the apparent size of that source is basically the same as the size of the sun in the sky, about plus or minus a quarter of a degree. And next to it, we have the module we're going to test. This is one of the latest Insolite Hyperion modules to arrive here in Madrid for us to test. We're gonna try to take an IV curve of it in a second. And below that, we have some sensors. On the one hand, for measuring the radiance, we use a reference module with all of the concentrating optics and solar cells matched exactly to the Insolite technology. This reference module is taken outdoors to be calibrated against a pyrheliometer. And so we know exactly what current it should produce at reference spectrum and irradiance, so at 1,000 watts per meter squared and 1.5 AM 1.5 deeps. Next to it, we have a spectral sensor package. Basically, behind these 3 collimating tubes, we have 3 isotype solar cells, 3 calibrated isotype solar cells. Isotype solar cells are solar cells that have the same technology as the triple junction solar cells used in the module, but each one of those only has one of its subcells electrically active. So that they have spectral responses that are matched to each of the subcells in the triple junction cell under test. And so this allows us to ensure that the spectrum is balanced in the spectral bands for each subcell, the same way as it would be outdoors in reference spectrum. One additional factor when we measure Insolite modules, with a normal module, we would place it onto this structure and probably perform small changes in angle to align it to the collimated light source by maximizing the power produced. In the case of the Insolite module, we have an additional degree of freedom, which is the integrated tracking system, the fact that the entire backplane is mobile. So the first thing we do when we measure it is we perform an alignment process. So I'm going to show you that now, if you can come back out here. So within the Hyperion project, one of the main deliverables of the UPM is building another solar simulator like this one with some improvements, and that has already been installed at CSEM in Switzerland, and it will be used for doing production line testing of the modules in the pilot line. For that, we had to develop a custom software for quickly aligning the modules to the collimated beam. We do that by using the same hardware for making a power measurement of the module, but also interfacing our computer with the module and commanding it to make small movements and optimizing the power by moving the position. So to start an alignment, we can simply click here. Okay, so looking now from behind the module, we see that the first thing that happens is the module is instructed to perform a homing operation. It moves down to the edge of its range, and it uses this V-shaped structure to locate a specific point repeatedly. Once it finishes doing that, in just a second, it's going to move back up to the center. And now our simulator is going to start making repeated measurements at near the voltage, the maximum power point voltage, all the time, as you can see, commanding small movements in order to look for the highest power. These measurements are actually taken at only about 250 watts per meter squared. We reduce the flash power in order to maximize the flash bulb lifetime. It takes about 15 or 20 flashes at different positions in order to find the maximum point. Okay, now that we have the module aligned, we can go to our normal IV tracing software that's part of the Helios 3198 simulator, and we can make an IV curve. Obviously, I've already configured the software for the voltage and current levels expected from this module, so I'm going to go ahead and start making an IV curve. One thing that's a little bit different about this simulator compared to a normal flat plate simulator is that we use a multi-flash approach. It's a very fast flash that's very bright, but with relatively small amount of energy. And for each flash, we gather 1 point on the IV curve, as you can see. So the recharge time is fairly quick. In a few seconds, we can make an entire IV curve. And as you can see here, we have gotten, for this module, about a little bit over 160 watts, which is about what we expect. That's approaching 30% STC efficiency. So that concludes the virtual tour for today's workshop, and we can go now to questions.